The method of sections is one of two ways that we can find the forces in the individual members of a truss. The other is the method of joints, which we'll talk about in another video. So the fundamental concept is that if a truss is in equilibrium, then any segment of the truss is also in equilibrium. So the method that we're going to apply here is we're going to start like we normally do by finding the external reactions. And so we're going to follow our standard 4 steps here of doing a free body diagram, doing force and moment balances, any geometry and algebra that need to be done. And when we're done with this step, we'll have the external reaction forces. And so we'd have the 2 applied loads that we were already given plus the reaction forces. From here, we'll actually move on to applying the method of sections, which is we're going to start chopping the system apart. And so what we want to do is take that truss again, and cut it, for example, here. And now we can look at either half of this truss and treat it as a different rigid body, because we know that if one part of this truss, if the whole truss is in equilibrium, then one part of it would have to be as well. And so all of the forces that are drawn right now are things that we know. And now we're literally just going to solve this like we do every single statics problem. We're going to start by drawing a free body diagram. So if we were interested, say, in the forces in the bar and the members here in the middle, we could draw a free body diagram that looks like the right-hand side of this truss, along with the cut-off members, like so, each of which now would have a force in it. And so we've got the known reaction force and the given applied load. And we're going to add to it now 3 unknown forces that are the tensions or compressions in the bar. I tend to just assume everything's in tension and then just let the minus signs come out in the end, and that way I don't have to think too hard about it. But you can, if you want to use a little bit more intuition, decide if you want to assume things are in tension or compression by flipping these answers. Just remember, if we guess wrong, we'll just get a negative answer, and that tells us that if we assume compression, it's really in tension, or vice versa. So once that's done, now we're going to write our moment balance, or force and moment balances, right? So force and moment balances. And this really is just like solving a rigid body problem. I think it'll be useful to add some labels here real quick, so let's do that. This is going to be joint A. We'll call this one over here B. We got C, D, E, and F. So this will be AY and AX. This will be BY, and these were given as F1 and F2. That's all for a coordinate system that looks like this. And the reason that's important is we want to use some labels over here now. We got BY, we got F2. This one we'll call force DF, so it goes from D to F. This one we can call CF, and this last one we can call CE. One of the things I want you to notice is these two forces still come together at point F, even though point F is not in our system anymore. So take a quick look at this, and you'll notice there are 5 forces, but we know 2 of them, so we have 3 unknowns, and we can generate 3 total equations. That's one of the big tricks when it comes to the method of sections, is that we need to cut only the number of members that we could write equations for. If you cut more than that, you won't be able to solve it directly. So we write our force balances, right? We got the sum of forces in the x direction here, which look like negative CE, since it points to the left, negative CF, the x component of it, and negative DF. And then we have F2 pointing to the right, and all of this has to equal 0. In the y direction, we have CFY pointing up, and we have BY pointing up, and that equals 0. And now we need to sum moments. And the trick is, if we pick the point F where the other two forces that are unknowns come together, we make our lives easier because a bunch of the unknowns don't show up in the analysis, and so we don't have to deal with them. So what we want to do is we're going to do minus CE. That one creates a moment, and it's going to be clockwise about F. We need this moment arm here. We need this moment arm here, and so that was actually given in the geometry of the problem as 4 meters. By the way, this horizontal distance between these 2 points was given as 2 meters, and this one was 3 meters. So we'll use that here as we do the moments. So we've got CE, and that has this vertical moment arm of 4 meters. And then we have BY. It's got a horizontal moment arm of 2 plus 3 meters for a total of 5 meters. And the beauty is all of the other forces in this pass through point F, and so they don't create any moment. From here we would move on to the geometry phase, just like usual. Where in this case we need to get CFX and CFY written in terms of CF itself. So we've got CFX would be equal to CF times the cosine of some angle, say this one here, and CFY is going to be CF times the sine of that angle. And so now we've truly reduced this to the 3 unknowns. And so from here we would move to step 4, which is do some algebra. And we'd be able to solve for CE, CF, and DF and get all of these unknown. So when is this useful? This is useful anytime you have a truss, but maybe you only care about some of the members. Right? If we only need to find some of the forces, we don't want to have to do the method of joints where we're solving a force balance at every single node. The other time that this is useful is sometimes we can use this to solve statically indeterminate problems that have more reaction forces than we can solve just doing the external forces. Turns out if you slice the system creatively, you can actually find unknown reactions by doing it one section at a time. That being said, you can repeat this process to solve more of the body as well, but in general it's most useful when we have a lot of members but only care about the forces in some of them.